Okay, so everybody flipped 50 different kisses, and so everyone's p hat is going to be different. But remember that your point estimate in this case would just be your p hat. So can someone give me an example p hat just so we can work with it? 0.3. Let's use that one. Okay. So for example, this one group had 30% of their 50 Hershey Kisses land on their base. What was your population? Yeah. So all Hershey Kisses. Your sample was 50 Hershey Kisses. Yeah.
Is this supposed to be our estimate or what we actually got?
What you actually got, yeah. Your parameter is the true proportion of Hershey Kisses that land on their base.
There's not 30% from the sample size, just has to be 30 and 30.
Yeah.
That's for me. It's not 7.
So remember that the parameter is always belonging to the population. So the parameter will always either be a true proportion or a true mean. Okay, in this case, it's just a proportion. So your statistic would be your p hat. So in this case, again, it's 0.3. So the statistic is what's trying to estimate the parameter. Okay, so we're going to assume this was a random sample. Anybody remember why random samples are important?
So you can generalize the population.
Very good. Okay, so random samples let us generalize to the population. So in number 4, that's just from your formula chart. So what we were using last unit was that the standard deviation of p hat was the big square root of p times 1 minus p over n. And what condition do we always have to check before we can use this formula?
10%.
Yeah, 10% condition. So you could say something like assume 50 is less than 10% of all Hershey Kisses. So remember, the 10% condition is just letting us check for independence, even though we're not sampling with replacement. So checking for independence there. But on number 6, we don't actually have the value of p to use that formula. So instead, we're going to use p hat. So your new formula would be big square root of p hat times 1 minus p hat all over n. If we had true p, of course we'd rather use true p. But in this case, we don't have true p. We only have our estimate. So we're going to use p hat. And in this case, when we use p hat instead of p, this is usually referred to as standard error. So in case you ever see that, that's why there's the change, is because we're essentially estimating p. So it's just a little bit different. Okay, let's see. What did you guys get for your standard error when you use 0.3?
0.065.
Okay, so everyone's will be different, but this is theirs. Okay, are you guys good up to here?
Yes.
Okay, so last thing is, would it be appropriate to use a normal distribution to model the sampling distribution? And the answer here is yes, because we meet the approximately normal condition. And remember, because we're in proportions, the normal condition, we have to check large counts. So you would do your sample size, so 50 times your p, so times 0.3 for me, and 50 times 1 minus your p. And check and make sure that these are both greater than or equal to 10. And you'd say, so therefore, it's approximately normal.
Wait, for the n, would it be using 5 instead of 50? Because for like the sample, like when you do it on the app, it only gives you 5 Hershey Kisses.
Yeah, so we did 5 at a time, but 10 times total to get a total of 50. Yeah.
I see, thank you.
Okay, so just zooming out real quick here. When you do confidence intervals, when you do a state plan do conclude, that's what we're going to do for every time we do a confidence interval. In the plan section, we're going to have 3 total conditions every single time. And so essentially the condition that we're adding is the random condition. So on your notes, star number 3 and say this is condition number 1. your random condition. You always want to make sure that your sample is random so that you can generalize to the population. And then on number 5, star that one. This is condition number 2. You always want to check the 10% condition so that you can use your standard deviation formula, which is built on independence. And then star number 7. So number 7 is your normal condition. So it's condition number 3, making sure that our sampling distribution is approximately normal. Okay, so let's do this next one, number 8, together. So before we do number 8, I'm just going to write this down. You don't have to write it with me because we'll see it again later. But to find your margin of error, which we know is part of our confidence interval, we do 2 things. We're going to multiply our standard deviation and multiply that by what's called a critical value. And so critical values is what we're going to practice finding in number 8. So I'm going to tell you what those are and we'll try them. Okay, so remember, back to your empirical rule from chapter 2, we said that in a normal distribution, 95% of the data lies within how many standard deviations? 2. 2 standard deviations. And so we'd say this is called a critical value, the value of 2, saying that 95% of your data is between these 2 places. I have to break it to you, that empirical rule had a little bit of rounding in it, so we'll find more precise critical values here in a second. But essentially what's happening is this 95%, that would be like our confidence level for our confidence interval. So your critical value is coming straight from your confidence level. So let's look at the first one, 80% of your data. So I'm going to draw you a picture. Oops, here we go. Okay, so imagine that we want 80% of our data to be within, and then how many standard deviations does that mean? Well, we'll figure that out. So how much is left over? How many percentage points are left over? 20, which means how much in each tail? 10. Okay, so there's 10% in that tail. So what I can do, in order to find the critical value, or essentially you could also think about it as like the z-score, in order to find the z-score where my arrow is, I can do inverse norm with an area of 0.1, mean of 0, standard deviation of 1. And that's going to give you what we call our z-star, our critical value, for an 80% confidence level. So when you do that, you should get like 1.28. So 1.28 would be your z-star for 80%. So you guys try the next 3, and then we'll check them together in a second. Oh, I should have mentioned, we always take the absolute value. So I know it's like negative 1.28, but just take the absolute value, and that's how we get positive 1.28.
For the standard deviation, it's actually 0.056 because n was 50, but we used n plus 5. That's why it's like. Oh, you did 50. Oh, because I calculated it again. I got 0.05. Because the one that she showed us was lower too.
Okay, so did you guys get 1.64, 1.96, and 2.58?
Yeah.
Okay, great. So these are all of our critical values. So anytime you need a critical value, you're just going to use an inverse norm and find one of these. These are our most common ones, though. So
Wait, I did the same thing and I didn't get that. So I just go to any norm and then put like the number as like area.
yeah, so like for the last one, I have inverse norm and then 0.005, comma 0, comma 1.
Wait, what? Can you repeat that?
Yeah, I have 0.005, comma 0, comma 1.
0.005.
Uh-huh.
What? Oh, so you're doing the part that's not in it?
Yeah, so like I'll draw you a picture for this one. So for example, for this last one, we've got 99% of our data on the inside.
Right.
So what I'm going to plug into inverse norm is the amount left in one tail. So since there's 1% left over for both tails, half of a tail is half of a percent, essentially. Yeah.
I understand that thing.
Okay, so now we can calculate the margin of error for your confidence interval. So to find your margin of error, you're going to take, since we're doing a 95% confidence interval, everyone's going to do 1.96 and then times whatever standard deviation that you got. So for mine, let's see, what was it? 0.065, let's see. So whatever your standard deviation times your critical value is your margin of error. So mine was 0.1274. So to find then your entire interval, you do your point estimate plus or minus your margin of error. Okay, so let's collect some confidence intervals. You guys don't have to write this down. I'm just wanted to show you how everybody's confidence intervals differ. You could take a picture of it once I draw it if you want to, or you could draw it with me. But I just want to have a few of us put our confidence intervals on the graph here. So I'll do this one first. So let's see. So 0.17 to 0.42. So my confidence interval looks like that. So the dot in the middle is my p hat, which is smack dab in the middle of my confidence interval at 0.3. Can someone shout out another confidence interval?
Can you draw first?
Oh, yes. Is that enough or further?
Yeah, that's good. Thank you.
Let's see. Anybody else get another confidence interval? Arya, how about you?
0.30 to 0.58.
That was
0.30 to 0.58. Okay.
margin of error.
Okay. How about you guys? What did you guys get? Yeah.
0.156 to 0.404.
Okay. Can someone call out another one?
0.09 and then 0.31.
Okay. Okay. Any others? Yeah.
0.208 to 0.471.
Okay.
20 minus 11.
Okay, so by the way, if you were to do this many times, you would get that the true proportion of Hershey Kisses that actually land on their base is 0.35. So notice how only 4 out of the 5 confidence intervals actually capture the true proportion. But remember, since this is 95% confidence, so what that means again is that if we had many confidence intervals, we would expect 95% of them to actually capture the green line, the true proportion. And 5% of them probably wouldn't capture the green line or the true proportion. So just remember, that's what the confidence level means. So the true proportion was 0.35. Okay, so let's sum it up. Oh, actually, take a picture of this if you'd like to. If you weren't drawing it out, you can go ahead and do that. Okay, so let's sum it all up. So, important ideas. I'm going to do 3 different sections of important ideas in case you're deciding how to split up your box there. So, important ideas. Number 1 is all your conditions. So, 3 conditions every single time. We've got our random condition, the 10% condition. For random, you're just checking to make sure, do I have a random sample? Yes, I do, or no, I don't. And last but not least, you need it to be approximately normal, which since we're working with proportions, in this case, it's large counts. Next time we'll work with means, and so we'll go back to central limit theorem and other stuff like that. But in this case, it's large counts. Okay, so in the second box, let's do your general formula for a confidence interval for proportions. So it's always going to be your point estimate or your statistic plus or minus your critical value, which in this case it's a z star because we're working with proportions with the normal model, times your standard error. So p hat times 1 minus p hat all over n. So statistic plus or minus critical value times standard error. And that in words is on the front of your formula chart. But so when it says statistic, you just need to know, what do I use for my statistic? When it says standard error, you just need to know, what should I use for my standard error? And things like that. But in words, it's there for you. And last but not least, let us make a note about your critical value. So I'm just going to say use inverse norm to find your critical value. And it's based off of your confidence level.